live. Okay, today, 316, we're doing max min story problems, okay? Okay, so because it's a cone and the volume is, so just think about a tap. So when you open up the tap or a hose, the volume going into the cone is consistent, right? The volume is like you just turn it on, so the amount of water doesn't go any faster or any slower. It's a constant rate. Does that make sense? Turn on the faucet, it's just filling up. However, because it's a cone, the rate of the radius of the height changes, right? So the height initially goes shh, right? And then as it gets bigger, the height would kind of slow down. It's still filling. Does that make sense? You pour it in there, and initially it's going to go shh, right? And then as you get fuller and fuller and fuller, it's still increasing, but it's still filling up, but at a less of a rate, okay? So let's take a look at this. So water flows into a conical tank 100 centimeters wide. So let me do that first. I want to put this, the tank itself is 100 centimeters wide, okay, and 250 centimeters deep, okay? The volume of the water, so find the volume of the water as a function of the height. So before we do anything, though, we get a little bit of something. We know the rate of the water. So the volume, I'm going to start here, can be expressed as 40 T. Okay, I'm just start there. 40 T. Every second we get this much water. The faucet's open. Every second we get this much water. 1 second, 40, 2 seconds, 80, so forth, so on. Okay, so the volume is increasing at this rate. Okay. What we need to do is find the volume of the water as a function of the height. Okay, so now to get the height of the water is changing. The height's not 250. The height is not 250. The cone's 250, but the water is, its height is changing. It's getting bigger and bigger. So it's a variable height for the water. The variable height for the water. Water is growing, so it's a variable height, okay? Well, what I probably need is a formula for volume. So I'm going to go, okay, volume is, of a cone is pi r squared h divided by 3. And the reason I needed that formula is because I'm looking for the volume of the cone with respect to height. So I need a formula with height in, okay? And this is the water. That's the water, which is a variable height because it's increasing, right? Okay, now I do know that I can put 40t here, right? Because I want the function of time. So I'm going to replace this, my 40t there, because that's my volume, right? So I'm going to go ahead and put my 40t equals pi r squared h divided by 3. Now, here's a dilemma. We have too many variables. We have too many variables, okay? We really do. We have t, r, and h, okay? We have too many variables. And I do know this. As the height increases, okay? As the height increases, so is the radius, correct? As the height's going up, so is the radius, okay? But what I want to do then is somehow kick the radius out, because I want this in terms of height. So I got to get rid of the radius and everything in terms of h. How do I do that? Well, we're going to go back to geometry, okay? What I see in here is the shape of the water. So the shape of the water has the same shape of the cone. Even though the water is constantly, it's getting taller and taller and taller, the shape of the water is it's a cone, right? So then what I'm going to do is go back to geometry, and the radius of this is 50. I'm going to do that on purpose because I need radius, okay? Okay, that I'm going to change that to 50 because I need radius, okay? So I have a ratio between similar triangles. And this goes back to geometry, but I have a similar triangle here to a similar triangle here. So I'm going to set up a ratio. I know that the radius of the water corresponds to the radius of the cone. Okay, the radius of the water, which is changing, that's why we use R. The radius of the water corresponds to the radius of the cone, as the height of the water corresponds to the height of the cone. Okay, so I set up a little ratio. The ratio between the radius of the water to the radius of the cone equals the height of the water to the height of the cone. Okay, now, what do I want to do over here? I want to think in terms of height, don't I? Right? So what I need to do is solve for R. So I'm going to solve for R. So I'm bring up my 50, and I'm going to have R equals 50h over 250. And I'm going to reduce this to R equals h over 5. You okay with that reducing? Okay, 1/5. So now I can do a substitution. So I'm going to take my h over 5 and plug it right there. So let's see. I'm going to rewrite this as a 40t equals a pi times my h over 5 squared times h divided by 3, okay? And that is technically, we're getting close to the right answer, okay? What do we need? We're getting close. We want the height of the water, function of time, represent height as a function of, so I need h, I need to solve for h. I need this, I need h of t. Okay, I need h of t because of that expression, okay? I need h of t. All right, so I got to solve for h. It's kind of a mess, but I can solve for h. I can. All right, so the first thing I'm going to do is multiply by 3, okay? Just get rid of this. Multiply by 3, okay with that? So get rid of it. So I'll have 120t equals pi times h cubed over 25. Don't freak out. I'll show you how I got that. Hopefully you see it. Okay? You see the h cubed? Okay, I see the h cubed and the 25, right? Okay, let's keep solving it. I'm supposed to solve for h, right? So let's multiply by 25. I don't know. Hold on. Calculate 120 times 25, and I get an answer of 3,000. 3,000 t equals pi h cubed. All right, I'm still solving for h, right? So let's divide by pi, divide by pi. So I've got my 3,000 t over pi equals h cubed. And then finally, let's just cube root both sides. So I'm going to have then an answer of h of t. H of t equals the cube root of my 3,000 t over pi. Okay? So, my question was, so we can go back to what our question was, and that's my answer to the first part, okay? My question was, represent h as a function of t. I need h of t. I'll have h of t. Okay, now, how does this help us? Well, at this point in time, at what time will the tank be full? Okay, that's a relevant question because if I were to say walk away and go do something and the tank's still filling, I got to time it so I can come back, or I can just, like the coffee pot, I could just sit there and stare at it. That's kind of what I do every morning. Right? What a waste of time, right? Actually, the truth is I just run to the shower real quickly and I got to time down. So the tank will be full when the height is 250, right? You guys agree with that? When the height is 250, the tank is full. So if I put 250 into this equation, I go 250 is the height equals the cube root of 3,000 t over pi. Okay, the height, it's full when it gets to its highest height, which is 250, and let's just solve for t. Okay, so first thing I'll just multiply by the pi, and I'll get 250. No, I'm sorry, cube it. Come on, cube it. Cube it. Let's see. All unclear. 250 cubed, and I get that answer. 156,250,0 equals 3,000 t over pi. I'll multiply this by pi, times that by pi. Get that answer. I'll divide that by 3,000. And there we go. 16,362 seconds. So this is a great problem. You know why this is a great problem? Do you really want to sit there and wait for that thing to fill? So let me divide that by what? That's in terms of seconds. Let's divide that by 60. Okay. Divide that by 60. And so you're really looking about 4.5 hours. Heck no. Turn the hose on and go do something fun, right? Absolutely. Okay. Let's turn the page. I think actually the funny part about this being a math problem is you'd probably be watching going, I got lots of time anyway, right? You wouldn't even do the math in real life. You just go, okay, I got a while. Okay, let's turn the page. All right. Example 2. So we've got a parabola. Here's my parabola. Right? And with this parabola, okay, you can do this on computers. It's kind of fun, right? You can actually take this point and you can move this point. As you move this point, the rectangle changes, doesn't it? Right? If I put the point here, if I take and move this point around, then if the point's here, the rectangle will be here. If I take the point, move it here, the rectangle will be here. So it's kind of like a cursor. I can move this point up and down, up and down. It would change the shape of the rectangle. Does that make sense? Okay. So what we want to do is express the perimeter of the rectangle as a function of the x-coordinate. Okay, so we know what we need is perimeter. Okay, so I know this would have to be some x value, right? And I know this would have to be some y value, right? If I have a point x, y. And this changes. That's why we're going to call it x, because depending on where you put the cursor, move it up and down, these values change. So let's call it x and y, right? Because if it's here, it's a different x value, different y value, vice versa, okay? Same time, we're talking about perimeter, which is a length, so this would also be an x. We're not going to call it a negative x because we're talking about perimeter, length, right? What's the length? And this would also be a y, okay? Well, perimeter, right? We're going to add up all the way around, so this is also an x and that's also an x, right? So perimeter, right? We're going to add up all the way around. So my perimeter is going to be a 4x plus a 2y, okay? All right, no problem, except we want to express it, we want to express the perimeter as a function of the x-coordinate, okay? So we want p and x, but we don't want a y. So somehow we have to kick out the y. Now I'm hoping you see what we're going to do. Do you see it? Something for y? Let's take 16 minus x squared and put it there, right? If we do that, then everything's in terms of x's, which makes sense because the perimeter binds the rectangle anyway. Okay, so let's substitute. Let's take 16 minus x squared and plug it in for y. Now, p of x, right, because all my variables x, perimeter with respect to x is equal to a 4x plus a 2 times a 16 minus x squared. Okay, how am I doing? And then I'm just going to, simplify this. I'm going to go 4x plus a 32 minus a 2x squared. Okay, how's that? So far, so good? Thumbs up so far? Now, domain. Domain's actually a really easy question if you know what's going on. Domain is the x values, right? Well, what's the smallest this x, think about this rectangle, what's the smallest this x can be? What if it's all the way to right about here? What's the smallest x could be? 0, right? But let's make it bigger than 0. Let's go x has to be greater than 0, because if it's exactly 0, we don't have a rectangle. You guys okay with that? What's the biggest y can be? Or x can be? X can go all the way over to right here, right? Well, that would have to be 4. I know that from the parabola, right? So if the x value is all the way here at 4, it can't equal 4 because then we wouldn't have a rectangle, so I'm going to say greater than 4, okay? So that's my domain, all the values of x, okay? Okay, lastly, what is the x value that maximizes profit? Well, okay, let's just graph it, right? Let's graph it, so I want to maximize it. So I want to make this the biggest rectangle I can, because there's several different types, right? You can have a rectangle here, you can have a rectangle here. Let's find the best rectangles that maximize the perimeter. So let's graph this. I'm going to graph it in terms of x. I'm going to graph, clear that, and I'm going to put in my y equals my 4x plus 32 subtract 2x squared. And let's maximize. Well, I might have changed my window. I'm sure I will. I don't need 50 on that. Probably, well, I know I can go 4 because I know my domain. I'm going to go maybe 25 and see what happens, okay? Okay, I'm going to fix my window a little bit. 0 to how about, I don't know, let's go 50. My maximum value is right about there somewhere, right? So I'm going to use my maximum feature, my calculator. These are good, rich problems. You know I'm a math nerd, don't you? When I like these kind of problems. I think these are super cool problems. So I get about 1 and 34. Okay, so my value, my point is 1 comma 34. What does that mean? Well, that's xy, but x is the x value, right? That is my x value. And then my 34 is my perimeter, because that's my p, that's my perimeter. Okay, that's all I have. Super rich problems. Love it. Okay, so you probably would love some help on homework, wouldn't you? Stop that. Come on, stop. Stop. Come on. Stop.